Hold on to your hats, calculates. We've got a big one today. 4.2, area, part 2. We're trying to find two approximations of the area of the given region below that lies beneath the graph of f of x, negative x squared plus 5, which is this curved line, and above the x-axis between x equals 0 for the vertical line and x equals 2, which is the end here. So we're going to approximate the area under this curve because we don't know a formula for area under a curve, but we do know formulas for area of rectangles. So we're going to divide up this region into 5 subintervals, and notice the right-hand corner of the rectangle is touching the curve. Okay, so we are going to do this process. First, determine the width of each rectangle. A is the left endpoint, and B is the right endpoint for all of these problems. So A is the left endpoint and B is the right endpoint. B minus A over n. N will be the number of intervals. So in this case, n equals 5. N is the number of subintervals. So we have 5 subintervals or 5 rectangles. So B minus A over n is the width of each rectangle. 2 minus 0 over 5. So you can see that the width of each rectangle is 2/5. 2/5, 4/5, I might as well write them in. 2/5, and that will be 4/5, and that's 6/5. So you can see that the number 1 is right there, which would be 5/5, and then 7/5, and then 9/5. My 2's in the wrong place. 9/5. Okay, so 0 to 2 is our, 0 to 2 is the region that we're finding the area between 0 and 2. Determine the value of each right endpoint. Oh, I just did that, sorry. Worked a little ahead. So using this notation, x sub 1, I is the counter, it's like a counter to tell which rectangle we're talking about. X sub 1 would be b minus a over n times 1. So that's our 2 minus 0 over 5 times 1. So there's our 2/5 that I have for here. And then x sub 2. X sub 2, I is the counter. b minus a over n, which is 2/5 times 2. So 2/5 times 2 is how we get 4/5. Now I know that this math seems pretty easy right now, but oh, did I count wrong here? See, doing easy math here. 2/5, 4/5, 6/5, 8/5, 10/5. So I did have my 2 in the right place. I just can't count. 8/5 and 10/5 is 2. So that's going to be right there. All right. Way to go, Lammers. So x sub 3 is 2/5 times the third. So that's where we get our 6/5 from. And x sub 4 is 2/5 times the fourth rectangle counter. So that's your 8/5. And then finally your fifth rectangle will have an endpoint at 10/5, which is 2. So I wrote a 2 there. All right. So the reason we go through those steps using this formula is because eventually we won't have numbers in all of these places. We won't have a counter. We won't know how many subintervals. We always will know b minus a. So if you're a big picture kind of person, that's where we're going with this. We're going to know b minus a, but n and I are going to continue to be variables in the future in like 2 examples. But for right now, we're using numbers. Then it says determine the height of each rectangle. Because if you want to find the area of a rectangle, you need the width of it, which is our 2/5 here. This is our width of the rectangle. And we need the height. So looking at rectangle number 1, the height of the rectangle. We don't know anything about this left side, but notice this right side touches the curve. And we know the x value here. So if we could find that ordered pair, we know the x value is 2/5 on that curve. What's the y value of that curve? Because that's the same as the height of the rectangle, because this distance right here is the height of the rectangle. So if we could find that y value, hey, we can, because we know the equation. So f of x sub 1, which means we're going to use the first x value, the right-hand side of that first rectangle, and we're going to plug it into our function. So we're going to have negative and then 2/5 squared and then plus 5. So 4/25 negative 4/25 plus 5 is 4.84. So the area of rectangle number 1 is 4.84 times the width of it, which is 2/5. So this is the height, that's the width, and that's the area. So let's find the height of rectangle number 2. Here's rectangle number 2. The x value that corresponds to the side of the rectangle that touches the curve is 4/5. So we're going to do 4/5 squared and then a negative on that and then plus 5. It's 4.36. So area number 2 is 4.36 times, is the width still 2/5 or did the width change? Notice these widths are all the same. Okay, eventually the widths will be different, but that's a whole different lesson. And then a sub 3, we need the height of rectangle number 3. So the x value that corresponds to the right side of rectangle number 3 is 6/5. So that's how we can find that height there. So negative and then 6/5 squared plus 5. .56. So the height is 3.56 and the width. Now did I put 4/5 here? If I could hear you, you'd probably be yelling at me here. The width is still 2/5. Just the x value changed for plugging in to find the height, but the width is still 2/5. Sorry about that. I'm just trying to keep you on your toes or thoroughly confuse you so that you need me more. Just kidding. It was an honest mistake. All right, then we're putting in 8/5, which is the right side of this rectangle, rectangle number 4. So the area of rectangle number 4 is 2.44 times 2/5. And finally rectangle number 5. So you plug in the x value, which in this case is 2. I can do that one without a calculator. So to find the area of each rectangle, we multiply our height times our width, and then we're going to add all those up. So I'll just do that math and you do it with me and see if you get the same answer. I got 6.48, and that's an approximation of the area under this curve using rectangles. So it's the exact area of these 5 rectangles, but it's an approximation of the area under the curve because we're missing all of these pieces here. So we really don't have the complete area filled in. All right, double check my answer to see if the right thing. I think I'm good, but you know, you can tell me tomorrow in class if I got it wrong. 6.84 or 48? I thought it was 6.84, so I may have made a calculation error. Double check my math here. Oh, false alarm, we're right the whole time. All right, so that is the approximate area under the curve using rectangles that have the right endpoint on the curve. We could do the same thing with the left endpoint on the curve. So this left part is the one that's on the curve instead of the right endpoint. Now, will this approximation be higher or lower than the actual area under the curve? If we're adding up these rectangles, notice the rectangles have all this overlap. They're higher than the actual area. They won't even match up. Well, we're ending here, so this area will be larger than the actual area. In the previous example, our area was lower than the actual area. Our width will still be the same, so that formula b minus a over n is still going to be 2 minus 0 over n, so our width will still be 2 over n. The value of each left endpoint, so the left side is 0, then we go to 2/5, and then 4/5, and then 6/5, and then 8/5, and we don't need this one on here, which is the number 2. We're just using the left endpoints. So this is x sub 1, and this is x sub 2, x sub 3, x sub 4, and x sub 5. Then we need to determine the height of each rectangle. So f of 0, remember our function was negative x squared plus 5. So f of 0 is 5. And then f of 2/5, we had that from the previous example. It was 4.84. And then f of 4/5 to find the height of the left side of the third rectangle. F of 4/5, is 4.36. F of 6/5 is 3.56. And the last one we need is f of 8/5, which is 2.44. So we already did most of that math. And then for our area, we will multiply the height times the width of each rectangle. And the width again stays the same. And you crunch your numbers and I'll crunch my numbers. And I get an area of 8.08. So the actual area under the curve is somewhere between 8.08 and 6.48. That's the area of the region that we really want. It's between those two values. So looking at the area of a generic rectangle, let's say rectangle that has an x value underneath it of x sub I, so the first or second or third rectangle, b minus a over n was our 2, that was 2 minus 0 over n, so that was our 2/5. But we're going to use 2 over n because we don't know how many rectangles we're going to have. And then I is the counter. Remember, we multiplied 2 over 5 times 1, or 2 over 5 times 2, or 2 over 5 times 3. We could do left or right endpoints, but we're just going to focus on doing the right endpoints. We don't have to do both, so we'll just pick one, and the right one is a little easier to do. So the x value we're going to plug into our generic rectangle is b minus a over n times I. And we're going to put actual numbers in here, but the n and the I are going to stay generic. They're going to stay variables. We're going to plug that into our original function, and that's going to represent the height of the rectangle, just like we were doing with numbers. We had a number and we plugged it into the function to get the height, but now we're not going to have a number to plug in. And then the width is still b minus a over n. So I realize here I left it as an n. We had 5 subintervals, so that would be 2/5. But as we move forward with this example, with this concept, we're not going to know how many intervals we're going to use, because, thinking about this, how could we make this more accurate? What if we used 10 subintervals? Then we'd have less space that we're using that's not really under the region, or we'd have less space that we're not using that is under the region. So the more subintervals you have, the more accurate your approximation will be. Okay, so thinking about how many subintervals would you want to have? What would be the best number of subintervals? How about infinity? Infinity! Yeah, like my favorite AT&T commercial. So we're going to do infinite number of rectangles, and we're going to multiply their heights times their widths, and then add up an infinite number of rectangles. That's where we're going with this. So one thing I want to note, there's a couple of problems on your homework where your region doesn't begin at 0, like it could begin at -1, and then you're going to have to put a -1 or whatever that left endpoint is in here for the x value of your rectangles. So anytime your interval does not start at 0, you're going to plug that left endpoint here and then add on the x value, the generic x value here. All right. So here we go. The limit process of finding the area. This finds the exact area. It's not an approximation because we're going to use an infinite number of rectangles. So we have to find the limit as the number of rectangles approaches infinity. We're going to add up our rectangles. So there's our summation. And we're adding up how many rectangles? From the first one up to the nth one. This is our height. And this is assuming that the interval starts at 0. Okay, remember to put that number, that left endpoint, if it's like 5 or -2 or whatever, put that in here and add it on. But that whole thing is our height, and then this is our width. And we're going to multiply those two together. So we have to get a formula for this, formula for that, multiply them together, do the summation of it. So that's why you learned that summation notation or reviewed it. And then finally, last thing we're going to do is take the limit. Okay, it's a big process, but doable. Let's review a little bit of limits with infinity. If we're going to multiply 4 over 3n cubed times the quantity 2n cubed plus 3n squared plus n, and we want to find the limit as n approaches infinity, we can't do it this way, because if you do direct substitution, you have 0 times infinity, and 0 times infinity is indeterminate. Because 4 over infinity is 0, and then infinity plus more infinities is just infinity. So 0 times infinity is indeterminate. So we're actually going to distribute that in. So we'll have 8n cubed over 3n cubed plus 12n squared over 3n cubed plus 4n over 3n cubed. Simplifying, we have 8 over 3 plus 4 over n plus 4 over 3n squared. And now let's take the limit of that as n approaches infinity. Remember that the limit of a constant is just the constant, no matter what x or n is approaching. Here, 4 over infinity approaches 0, and here 4 over 3 times infinity squared also approaches 0. So our limit is 8/3. So just a review of that, you always want to multiply that in so that you don't have an indeterminate form. Let's go. The limit as n approaches infinity of the summation of 1 to n rectangles of 1 over n to the third times I minus 1 squared. So find a formula for the sum of n terms. That means you can't have the letter I in there anymore, and you want to get rid of the summation. So we're going to use our summation formulas. And then we're going to finally find the limit. So our first order of business is to rewrite this so it's not a summation and it doesn't have an I in it. It has to be all n's and no summation, okay? So our first step is to square that I minus 1. So I'm just going to take the part that we're trying to find the limit of and rewrite it over here. I minus 1 squared, remember to use FOIL. If you need to write it out, do it, but do whatever you need to do to get the right answer. And now we want the summation. If you have the summation of a constant times stuff with I, remember this is a constant for our purposes here because the variable that we are summing, this is the variable of the summation. This would be the constant at the top. So this is a constant. You can pull constants out of summation and just deal with them later. So then we have the summation of I squared minus 2I plus 1. And I squared, we have a formula for that, the summation of I squared. And then we can do, I should do a minus there. Summation is kind of like distributive. You can distribute it. And then we can do the summation of each piece. Okay, remember that constant we can pull out in front of that part. 2 times the summation of I, and then the summation of a constant 1. So we can do the summation of each of those. Now if that thought process is common sense to you, then you can jump right from here to the summation formulas if you'd like to. But I just wrote them out in case people are, this is new to them or they want to think through every step individually. So the summation of I squared. Remember our formula for that? I think we just reviewed them. The summation of I squared is n times n plus 1 times 2n plus 1 all over 6 minus 2 times the summation of I, which is n times n plus 1 over 2 plus the summation of the constant. Now, I don't know if I could say this enough so that students would never forget it, because I've tried to say it as many times as I can. The summation of a constant is not just the constant, it's n times that constant. And I can say that a million times, infinity times, and I bet students would still forget that. So if you are getting a wrong answer in a problem, go back and check to make sure you did the summation of the constant. It's an easy thing to forget because you're looking for those i's and using the I formulas, but there's a constant there that you have to use the formula for too. So don't forget that. Don't distribute that in yet. We're going to simplify all of this, but notice where we are now. We now have a formula that has only the letter n in it. So we have a formula for the sum of n terms. But we're going to have to do the limit, and so before we can do the limit, as n approaches infinity, we want to simplify this a lot. So 1 over n to the third times, I'm just going to distribute that in first, so we'll have n squared plus n, and then that's going to be distributed times the 2n plus 1. Here, these 2's can cancel, so I'll have minus n squared, and then that minus sign distributes. So as I'm distributing the n in, I'm distributing a negative n in. So negative n squared minus n, and then plus this n at the end here. Continuing to simplify, 1 over n to the third, and then this is 2n cubed, plus, using FOIL, n squared, plus 2n squared, plus n, and that's all still over 6, minus n squared, and then minus n plus n, I'm just going to add those together and get a 0 for that. All right, now I could distribute the n cubed in. So 2n cubed over, 2n cubed over 6n cubed. I'm going to split up that fraction too while I'm at it. N squared and 2n squared, if I add those together I get 3n squared, and then it's over 6n cubed. I forgot to write my n cubed here. So I'm distributing the n cubed in and doing a little simplifying as I go. You can pause it and catch up if you want. Multiply the 1 over n cubed times n over 6, we get n over 6n cubed. And then finally, 1 over n cubed times negative n squared is negative n squared over n cubed. Simplifying, cancel those, I get 1/3. Cancel 2 of those with 1 of those, I get 1 over 2n. Cancel 1 of those with 1 of those, I get 1 over 6n squared. And then cancel 2 of those with 1 of those, I get 1 over n. And now I have a simple formula of which I can just take the limit. It's all set up to take the limit as n approaches infinity. it will equal, remember the limit of a constant is 1/3. The limit of this as n approaches infinity is 0, another 0, another 0, so my limit is 1/3. Okay, let's step up the game a little bit. Let's use the limit process, which is also called the limit definition of area, to find the area of the region between the graph of the function and the x-axis over the given interval. So I have some function like that, going from -1 to 1, and I want to find the area under that curve. All right. Our limit process is this formula. Limit as n approaches infinity of the summation of I equals 1 to n of the function, and since our endpoint is not at 0, we have -1, plus b minus a over n times I times b minus a over n, and that one's not times I because that width stays the same all the time. B minus a, in this case, that's the width of our rectangle, is 1 minus -1. We don't know how many intervals, so we're going to keep it as an n. So 2 over n is our width. So we have the limit as n approaches infinity of the summation of 1 to n rectangles, and then f of -1 plus 2 over n times I, and that whole thing is multiplied by 2 over n. Our function is 1 minus x squared, so I'm going to put this in my function. So my area equals, and I'm going to get tired of writing limit pretty soon, so I'm going to stop writing equal signs. So -1 plus 2I over n, just a minute. Putting it in the function means I should start with the 1. This function starts with a 1, minus, and then -1 plus 2I over n, which is my x, squared. That is the width, and then times the, that is the height, here to here. It's the height of each rectangle, each generic rectangle, times 2 over n, which is the width. I'm going to keep simplifying, so I'm just going to use a big arrow here. I don't want to keep writing limit and the summation. But I do need to, first of all, think I'm going to pull that 2 over n out in front. I'm just moving the order of these two around. And now I'm going to do 1 minus and FOIL this out. So if you need to rewrite it in two separate factors, you can do that. But first times first is going to be 1, and then outside and inside added up is going to be -4I over n, and then last times last is 4I squared over n squared. So that whole thing is going to be subtracted from 1. So I have 2 over n times 1 minus 1, which is 0, and then minus the negative, so it's 4I over n, and then minus, so that minus sign, minus that one is 4I squared over n squared. Okay, I need to do the summation formulas now. So the summation of I, here's my 4 over n, that's from this part. Summation of I is n times n plus 1 over 2. Plus, minus. So definite, I said plus, and it's actually a minus. 4 over n squared, and then the summation formula for I squared, which is n times n plus 1 times 2n plus 1 over 6. So I have 2 over n, and then this n will cancel with this n, and this 2 will cancel with this 4, so I'll be left with 2 times n plus 1 minus, this n cancels with one of those, and if I cancel a 2 out of there, I'm left with a 3, and a 2 out of there, I'm left with a 2. Notice I'm only canceling things that are multiplied together. I'm not taking anything that has addition next to it. So we have 2 over n, because that 1 cancels with one of those. And then inside the parentheses, I'm going to FOIL this out. So it's 2n squared plus 3n plus 1, and that's still over 3. Continuing to simplify, I have 2 over n times 2n plus 2, distributing. And then distributing on the top, I'm going to have negative 4n squared over 3n, negative 6n over 3, negative 2, over 3n, and negative 2 over 3n. Distributing that 2 over n in, I'm going to have 4 plus 4 over n. So I'm multiplying this 2 over n in here, minus 8. That 1 cancels with that 1, so minus 8 n over 3n. These n's cancel, and that cancels to be a 2, so minus 4 over n, and then minus 4 over 3n squared. I can cancel those n's. Now I'm ready to take the limit. So I want the limit as n approaches infinity. How do I know I'm ready to take the limit? Because I've canceled everything and I have individual fractions. The limit of 4 is 4. The limit of 4 over infinity would be 0. The limit of 8 thirds, negative 8 thirds is negative 8 thirds. The limit of 4 over 0 is 0. And the limit of 4 over 3 infinity. Did I say 4 over 0? I meant 4 over infinity is 0. And the limit of 4 over 3 infinity is also 0. So I have 4 minus 8 thirds. So common denominator, 12 thirds minus 8 thirds. I get 4 thirds. All right, that's a pretty long process. And I know we won't want to do a lot of those problems, so there aren't a ton of them on your homework, but just be very careful with your math. Okay, we don't need to do this example. A basic area idea is that if you have area above the x-axis, it should be positive, and if you have area below the x-axis, it should be negative. So here's your homework. To do the midpoint rule, which is where the midpoint of the rectangle is the part that touches the x-axis. So if you have a rectangle, the midpoint of the rectangle would touch the x-axis. So our rectangle would be half over and half under. So we would want rectangles that all go a little bit over and a little bit under, so their midpoint touches it. You can use the midpoint rule program, which I think I gave to you yesterday, but if you didn't get it, let me know and I'll give it to you. That's for 77 and 79. Okay, so there's your homework. I know it's heavy stuff. Do your best. Keep trying, plugging along. Have a good day.